Hello everyone, welcome back to my YouTube channel. In previous video we did a simulation where we were using shared topology and we have seen that you don't need to do anything with the context. In today's video I'm going to do a simulation where we did our meshing with the non-shared topology and we will see how you have to deal with the context. I have already finished simulation. I will show you the meshing setting, context, and then I will show you the simulation setting. First of all, here is our meshing. It is our fluid region. This one is our base plate and these are our battery cells. You can see nodes are not shared between different region. Here is one thing that you can use really coarser mesh for the solid region and you can use finer mesh for the fluid region. This meshing is helpful when you have limitation from the computational power. You have to take care about one thing. The cell ratio between two different zones should not exceed 1 to 5. So here we have one cell and here we have more than 10 cell. Normally to get better results, ratio should not exceed 1 to 5 cells. And then you have to check your context. I have already created context. We can go through these contexts. Normally these contexts are created automatically. If they are not, you can create by yourself. I can show you the way. Let me delete these contexts. One thing, you can create contexts for different parts separately. Let me show you what I mean. For example, I want to create two context group. In one context group, I want to have contact of these battery cells and this base plate. In the other contact group, I want to have contacts for this fluid region and this base plate. Sometimes when you have really large number of cell zones, then it is a better practice to have separate context group. To create connection group, you can go over here, right click and say create connection group. So in this connection group, here you have seen all these bodies are being selected. So you can select a body which you want to create, which you want to have in this group. So I will select, for example, all these battery cells and I will select this base plate. Here now I have only 13 bodies and then I can right click and I can say create automatic connections. So it has created these connections. We will go through these connections. Let me create another one. I will say another create connection group. In this connection group, I want to have this 1, 2, 3, 4, 5. So 5, and then I will say create automatic connection. So one thing you can notice that for this one, for base plate and fluid, we have 4 contacts because we have 5 cell zone. Each cell zone have one contact with the base plate. And on the other side, if you come over here, we have 12 battery cells, 6 on this side, 6 on this side, and we have one base plate. It means we must have 12 contact region. But here you can see we have 28 contact region. It means we have a lot of extra contact region. We can see, and one thing before that, there is a gap between these two battery cells. All these battery cells, they are not connected with, but I think it is creating contact between these two. We can check. Yes, here you can see it has created a contact between these two battery cells. If you go further, you notice that it has created contact region between these battery cells. Although some contacts are correct, but there are few contacts which are extra. I want to remove all those contacts. You can do it manually, but there is a better way of doing that. Delete all these contacts. Let me delete all those one. Then come over here in the contact. Come in the slide bar. Normally with practice, I found out that if you put 70, so then it create a better contact region. So I have put here 70, then I will come over here and I will say create automatic connection. And here you can see I have 12 contacts. And that's fine because I was expecting 12 contacts between these 12 battery cell and the base plate. You can change them further. You can say create contact or rename based on definition. Now exactly you will know the contact between different cell zone. For example, battery cell 1 to solid base plate. Similarly, you can say create based on definition. Here you also have base plate with the fluid 1, 2, 3, 4. That's perfect. Then you come over here. Here I have some name selection which I use for the meshing as well as for inlet and outlet. Now we can move to Fluent and we can simulate. In Fluent I have already done all the setup and I have result. I will show you the setup. I have already done that because in previous video I have gone through all these steps, so I don't want to go it again. You can watch previous video for more detail. Here is our geometry which I have imported over here. I can show you the meshing. For that I will go into the graphics, meshing, new, node and edges, select all, and I will display. I'm showing this meshing because I had tetrahedral element in the meshing. In here I have converted all those tetrahedral into polyhedral that you can see over here. And you can check quality from here, which I showed you in previous video. Other than that, let me quickly show you the setting. In general, it is a steady state and gravity is not activated. In model, I am using energy equation and I am using K epsilon, standard wall function. Then in material, I have defined water glycol with these properties, and in the solid, I have aluminum and cells or battery cells. And I have shown you how you can define this orthotropic thermal conductivity. Then I have assigned these material to their respective cell zones. All these fluids, they have been assigned with water glycol. Similarly, in solid, I can show you a couple of material. Battery cell 1, if I go in here, battery cell 1, it has material name cells. Then in source term, I have defined one source and its value is 2700 watt per meter cube. I can say OK and close. Here is the base plate and it should be of aluminium. That's correct. Then in boundary condition, I have inlet over here, and in inlet the mass flow rate is 0.75 gram per second. The temperature is 20 degree Celsius. And then we have interfaces. I have shown you 12 interfaces and all these interfaces have been transported over here. If you like, you can display, for example, let me display this one. Here is the interface. This one is the between battery cell 1 to solid base plate. In the previous simulation where we were using shared topology, we didn't have any interface over here. Another thing in interface which is really important, sometimes you have contact resistance. You can say thermal contact conductance or the contact resistance, which you can define over here. I will show you maybe in next video how you can define contact resistance over here. Here I just want to show you there is an option available to do that. Close this one. Then in internal we don't need to do anything. In outlet we don't need to do anything. In wall, all these walls have been created automatically. So if you have any convection on the wall, you can define over here. On wall we don't need to do anything, and the method I am using simple. Control, I am not changing control, all these are default. I have defined two reports. Then in a report plot, I am plotting both of these temperature. The setup is same as in the previous simulation. You can check detail in the previous simulation. Then I have run the simulation for 500 iteration and the simulation have been converged. I can show you the results, the temperature, for example, the outlet total temperature, save display. Here is our temperature distribution for the battery cell. If you have seen previous video, you can see it is same as we did calculate in the previous simulation. I can show you the outlet temperature. In the previous one, the outlet temperature was, if I remember correctly, 23.7 something. We can check this one. For that, come over here at the report, surface integral, and we want to calculate the outlet temperature, but we want to have mass weighted average. We need temperature, we need total temperature, and we need all those outlets. We can say compute, yes, 23.718 or 72. And if I remember, we had exactly the same temperature in the previous simulation. You can see we have same outlet in both cases with shear topology and non-shear topology, but the only difference was here in non-shear topology we have created all those interfaces by ourselves, and we have checked if all those interfaces make sense. If you want to avoid that hassle, you can use shear topology, but as I discussed in the meshing of the shear and non-shear topology, both have some advantages and disadvantages in terms of meshing that you can check in the video. But from the simulation result perspective, both create same result. That's it for today. I hope you found this tutorial helpful. Thanks for watching and see you in the next video.